Friends, welcome to the 15th lecture in module 1, where we are going to now solve couple of example problems on planar non-orthogonal structures. We will also discuss the relevant computer codes with which the problems have been solved. We will explain the computer code steps and also the solutions obtained from the computer program. Let us quickly revive the steps in solving a non-orthogonal structure. The steps involved could be the following. For the given problem, first identify the Jn and Kn of each member. Friends, please recollect a very important statement. Identifying Jn, Kn is actually locating the xm, ym axis, which we call local axis of each member. So, while doing so, please understand that xm should be facing towards the positive length of the member and ym axis should be anti-clockwise 90 degrees from the xm axis. Okay. Locate the j and k end of each member. After doing that, let us compute the Cx, Cy, which are called the transformation matrix coefficients of each member. Also identify or label the degrees of freedom at each node. First, the unrestrained set of degrees of freedom, then the restrained set of degrees of freedom. We should do this. So, then I will know what is the size of each matrix of the member, what is the size of the complete total matrix of the structure. I will also know size of the unrestrained stiffness matrix of the structure. Okay. I will be able to do this. Now, I can have a clue. I think all of you will agree strongly with me. Since we are including the axial deformation in the analysis, hence the size of stiffness matrix of each member will be 6 by 6, okay, and the size of unrestrained stiffness matrix of the complete structure will be the unrestrained degrees of freedom. Okay. So, we have to be very clear about the size of different sub matrices in the given stiffness matrix. Okay. So, the next step is estimate the stiffness matrix of each member. We already have this equation with us derived in the last set of lectures. We know this is going to be a 6 by 6 matrix. We already have a fixed beam as our basic module. We know that this is going to be theta p, theta q, delta r, delta s, delta t and delta h, where this is my xm axis, this is my ym axis of the member. The member has length Li, E, I and A. Okay. So, we already derived the 6 by 6 matrix of each member. So, estimate this for each member. Okay. Also identify the global labels of each member Okay, that is very important. Once we have done this, then K global of each member, which will be T transpose K local T, because transformation matrix of each member is now known to us. Okay. Once I have this, then assemble. So, let us do this for every member. Assemble K matrix global of the complete structure, then plug out K bar UU submatrix from K total, K bar total. Okay. Then compute fixed end moments of ith member in local axis, find fixed end moment of the ith member in global axis, which will be T transpose of the ith member and fixed end moment of the ith member. Once I have this completed, then estimate the joint load vector in global degrees of freedom for the complete structure. From this, plug out the joint load vector of the unrestrained degree from the global joint load vector. Okay. Then use this equation, delta bar global will be actually equal to K UU global inverse of JLU global. You get delta bar unrestrained. Friends, it is very evident and you will understand and agree, delta bar R of the system will be actually a null vector. Okay, it will be 0, restrained degrees of freedom. Okay. After obtaining delta U, one can calculate the m bar of every member, that is the global end moments and shear of every member, from simply K bar of every member multiplied by delta bar of every member plus any fixed end moment of every member in global terms. Okay. So, we have to do this and identify the end moments and end shears. Let us take an example and solve this problem. Let us take example 1. This is my structural system. Okay, which is fixed here as well as fixed here. Let us call this end as A, B and C. Let us mark the dimensions of the structure. So, this is 2 meters and let us say this is 4 meters. Okay. Let the height of the frame be 4 meters. Now, interestingly, this is my global axis. And for every member, the local axis is going to be different. Okay. Let us say the I value, the moment of inertia of each member is 0.0016. This member also has I, this member also has I, E is constant, whatever may be the value, whatever may be the material, it is constant through and through. Okay. Area of cross section is 0.120 meter square, this is meter 4, which is also constant. So, A and A. Okay. Once we have this, let us say the system has a joint load which is 10 kilonewton applied on the structure. Okay. I think from simple geometry I can find this angle theta. You know, theta is actually tan inverse of 4 by 2, okay, which is going to be 63.435 degrees. Okay. By this logic, this angle is also theta. Now, let us fix up the local axis of each member. This is my first member, this is my second member. So, let us say the local axis of this member has the j n here and the k n here. Okay. And this becomes my x m and this becomes my y m. Similarly, for the second member, this becomes my jth end, kth end, and this becomes my x m axis and this becomes my y m axis. Okay. So, let us make a table and try to compute some information required for the calculation. Let us say member number, okay. What are the ends, that is the jth end and the kth end, what is the length of the member, what would be the value of theta and what would be the value of cos theta and sin theta, Cx and Cy, and what are the global labels of the member. Let us do this table. For member number 1, Jn is at A, is it not? Kn is at B. For member number 2, Jn is at B and this is at C. The length of the member AB is inclined, which will be square root of 4 square plus 2 square, which will be actually equal to 4.472 meters. The length BC is simply 4 meters. So, now xm is oriented this way from the global axis x anticlockwise, so positive. So, theta is going to be plus 63.435 degrees. As far as the second member is concerned, theta is 0 degrees. Okay. Let us compute cos theta and sin theta. This is going to be 0.447 and this is 0.894 and this is 1, this is 0, cos 0 1, sin 0 0. Okay. Let us now enter the global labels. Before that, let us mark restraint and unrestrained degrees of freedom. So, let us mark unrestrained degrees in green. So, let us say there will be a rotation here which I am marking as theta 1. There will be an horizontal displacement here which is and vertical. So, delta 2 and delta 3. Okay. These are the unrestrained degrees. The restrained degrees are going to be, let us say theta 4, delta 5 and delta 6 and theta 7, delta 8 and delta 9. Okay. So, now let us mark the labels global. So, let us say Jn Kn for the member AB. So, I should say the labels are 7 and 1, these are the two moments, 7 and 1. Okay. Then the next is along the y axis. So, 9 and 2. The next is along the x axis. So, 8 and 3. Okay. How do you label this? Take a fixed beam. Let us say this is x m, this is y m, is it not? So, 1, 2, then along y 3, 4, then 5 and 6. So, same style here. 7 and 2, 7 and 1 are the moments, then 9 and 2 are along y axis global, and then 8 and 3 are along x axis global. Similarly, let us do it for the second member. So, you can do it easily now. 1, 4, okay, 2, 5 and 3, 6, correct? It is done. After we do this, let us compute the rotational coefficients. Because we need them for the stiffness matrix. Let us do it for the member AB. You know, it is going to be 4 E I by L, which is going to be E I times 0.0016, okay, by 4.472. Similarly, 2 E I by L, which is 2 times 0.0016 by 4.472. This is for the member AB. We can also do this for the member BC, which is 4 times E 0.0016 by length of the member, which is 4.0, and 2 EI by L, which is 2 E 0.0016 by 4.0. Okay. Once I have these values, I can now enter KAB. I can find the stiffness matrix local of AB and stiffness matrix local of BC from the standard equation of 6 by 6, which we already have, which are meant for P, Q, R, S, T and H. Similarly, P, Q, R, S, T and H. Okay, we have this matrix with us, we know this matrix. Let us do it for KAB and KBC. Similarly, I can also now find the transformation matrix. Okay. Transformation matrix T of any member I is actually given by, it is a 6 by 6 matrix, okay, 1, then 1 and 0 0 C x 0 C y 0, then 0 0 0 C x 0 C y, then 0 0 minus C y 0 C x 0, then 0 0 0 minus C y 0 C x, okay, where C x and C y are available in the table here. You can see here we already have C x and C y for both the members. So, one can compute this transformation matrix for the member AB and for the member BC. So, there is no problem, is it not? I can also compute the transpose of this matrix for AB, the transpose of this matrix for BC, that is also a very easy problem. So, let us do this now. Okay. Let us complete this. After getting this,